helped design some of Honolulu's most complex structures, from Alfred Preis's Arizona Memorial to Vladimir Ossipoff's Diamond Head Apartments, the first precast, prestressed concrete tower in the country. Other notable projects include the Ala Moana Hotel, Kahala Hotel, and the IBM Building. He was president of Yee Precast Design Group, Limited in Honolulu, Hawaii, and director of Precast Design Consultants in Singapore. He was one of the most influential and innovative structural engineers in Hawaii's history. During his stellar career, he gained a following as a prolific innovator, holding more than a dozen patents for construction systems and devices such as the NMB splice sleeve mechanical connector and the concrete honeycomb precast framing system for large ocean platforms. Perhaps his most remembered quote is, "Nothing excites me like a difficult design problem that can be met by a simple solution." This lecture by Al Yee was given at the Friday noon meeting of engineers and architects of Hawaii on September 14, 2012. The lecture is on the design and construction of his tallest precast building, the Sail, on Singapore's Marina Bay, a 70-story tower completed in 2008.
My name's Howard Wigg. I'm current president of Architects and Engineers of Hawaii, which is over 100 years old. For you newcomers, we have a set regimen within engineers and architects, and one is to tell a joke. Do we have a jokester in the house?
Well, it's becoming more apparent that men need some guidance on how to communicate with the ladies. And it's, as we see, there are now books coming out to help us, training aids, other guidance to help us answer questions generally from the ladies that don't get us in trouble. We should never lie. Don't have to tell the truth. Not lie. And so I share with you this example. May be useful to you. Lady, it was in the form of a cartoon, one of the great ways to tell a story. A lady standing at the doorway with her, let's say a full-figured lady, standing at the doorway. Her husband is in the room adjusting his tie and tucking in his shirt. And she says to him, "Does this dress make me look fat?" And he turns to her and he says, "Does this shirt make me look stupid?"
I think all of us can relate to that. December 7th, 1941, a skinny 16-year-old kid is standing in the backyard of his Kaimiki house, watching Japanese Zeros fly so low overhead that he can see their goggles, he can see their leather helmets. He is convinced that they are going to land, put him in prison, and he will starve to death. Obviously, that did not happen to any of us. Fast forward to engineering school, structural, and getting a structural engineering degree from a little institution called Yale. Coming back to Hawaii, working with a unknown little architect named Alfred Preis, who has been commissioned to design the Arizona Memorial, come full circle back to Pearl Harbor. The reason that the memorial has a dip and an arise is the dip represents the nadir, the lowest point of the war, as in December 7th. The rise represents a rise to victory. Sounds good, except that this wedge is 184 feet long, and it's sitting over the memorial, the Arizona, which is shifting in the mud. Solution: stress or reinforced concrete, very much a pioneering technology at the time, in the shape of tuning forks, separated by 111 feet, but you're on this very, very unstable ground. What do? Even though the water is only 40 feet deep over the Arizona, you sink the piles down 150 feet for stability. We're talking about an engineering feat here. Fast forward to all around the Pacific, job after job after job, patent after patent after patent regarding reinforced encased concrete. And it gives me pleasure to first bring up Mr. Hans Kruk, who is working to this day with that scrawny kid terrified in Kaimake. Mr. Hans.
It doesn't look too scrawny right now. Thank you. It's been a delight these several years to work with Al Yee. We're working together to develop OTEC, and the key element to doing all of the work and make this thing a success is, in fact, Dr. Yee's platform. With that, we hope to be instrumental in a revolution in the Pacific about energy production, water production, and all the associated good results from the largest energy resource in the ocean. And Al is a delight to work with. Every morning he comes up and he has invented something new overnight. It's amazing. His brain never stops. And so I would like to introduce him to you, and one of his achievements is the wing, the structure, the sail, one of the tallest, thinnest buildings ever built, actually. He successfully built that in Singapore. So let me give it back to you.
Mr. L, the pal, Yee.
Thank you very much. Thank you all very much. I don't know how to start with this kind of introduction, so I just go on the subject matter. We practice structural engineering, and many times we are at the service of architects. The architects, require certain column spacing, certain directions of beams and slabs and spans and all that. And our job is to make it practical, make it buildable, and cost less. So in Singapore one day, we had a commission to design two buildings. And one building was 70 stories high, and the other one was 63 stories high. And these buildings were to house 1,111 condominium apartments. It was built right on the shores of Marina Bay, a very expensive, high-class district right near downtown Singapore. The architects from New York, NBBJ, which stands for Narramore, Bain, Brady, and Johansson. I know all the partners from the old times, and they're all retired now. And I was a little kid when I started working with them, so I'm following them closely. Anyway, they came in and mentioned that this very thin towers, for instance, Tower 1, the tallest tower, is 245 meters high. The floor plan is like a football. So it has a wider and a narrower dimension on the plan. And the widest plan portion is only 22 meters. So the aspect ratio is 245 over 22, which is over 11. And, not many buildings I know of have an aspect ratio of over 11. If you take a 12-inch rule, 1 inch wide, and put it on your table, and it's like that, that's an aspect ratio of 12. Ours is a little over 11, so you're talking about a very slender building. I can do the 12-inch high building, but I don't know if I can do a 840 feet high building. But then we warn you that we designed 5 of these projects, and none of them got built because the price was too high. They're so skinny. Many things you worry about in high-rise buildings. Number one is human comfort. That's the term I use, because you can get seasick if the building rocks. The the von Karman vortex. And the wind doesn't have to be high. It's just a normal windy. And you can have this vibration. So that's the biggest worry. Of course, we also worry about strength. Because in the year 2000, Taipei had a huge earthquake, and I went there to check some buildings for a client of mine. And I saw a high-rise building lay flat on the ground. It's like somebody going to sleep. I mean, just like that. It's scary. You see the windows, doors, the corridors, everything. And I said, wow. But anyway, I told the architects that if they pay attention to our suggestions, I think we can bring it in. Within the price, you're going to get it built. And so we started working on it. Let me show you some of the things. And this is an actual photo of the sale, which is this iconic high-rise building. And I got to get this thing. This is the 245 meters. And this cantilever from here to here, this bow sticks out 10 meters, about 32 feet. This guy here goes backwards. This is a 63-story building, and this is a 70-story building. And it's right on the shores of a beautiful Marina Bay, which is where the Sands Casino is located, financial centers, all kinds of things. Now, the layout of the floor plan, you have a mass transit operating there. And when we drive piles, we have to make sure that we do not move the tunnels more than like 10 millimeters. And very, very strict, because otherwise the transit will get, derailed. This is the 70-story building. This is a 63-story building. But this back half of the 63-story building bridges across the mass transit corridor, and so it's about 21 meters. This portion is only about 8 stories high, whereas this is 63 stories high. This building here is a swimming pool, recreation, landscape, tennis courts, and all that, and equipment room. This is 9 stories high, and that bridges across the mass transit. Now, the structural framing, this is where things get serious. I told the architects that we have to line up, these are bearing walls, and these bearing walls have about 3 or 4 functions. First, they're firewalls to prevent fire from spreading. They're privacy walls. You don't hear one person living in this apartment talking and the other guy can hear you. So they have privacy, fire. They carry the vertical load of the building, like gravity loads. It carries wind loads because you try to push it sideways with the wind, or earthquake. This will act very efficiently against any forces coming from this direction. And then you have some walls in this direction which act very efficiently against this direction. But you have a whole bunch of little columns, which is not shown in this drawing, but the columns that are 3.5 meters on center with a combination of the spandrel beams. So you have like a network. You'll see that later on the pictures. But they help resist this direction. That's the building going up. It's a 5-day cycle, which is pretty fast for this size building. And the precast, all the floor slabs are precast. The walls being so heavy, we couldn't precast them because the walls are 2 feet thick on the lower floors, going all the way up to 1 foot thick at the top floors. Now, the real strength of this wall is what I call a coupled shear wall. I'll describe that later. But when you analyze it with our computers, we find that the first mode is in the longitudinal direction. In other words, the building is softest in that direction. You would think that the transverse direction would be softer, and that would be the first mode. But anyway, that became the second mode. You can see the period of vibration here. And then this guy here, the torsional mode, is the third mode. Now, imagine your human body. You want to be able to resist this kind of force. You can resist this kind of force. But you don't want to be having your body twisted, like here, before the orthogonal forces strike you, because it'll break your spine. Well, the building has the same kind of feelings, because the columns, beams, and all that behave as your spine, you know. And so this verifies that we have a relatively safe building for earthquake. The earthquake intensity we use, although Singapore earthquake is not in the code. They don't have the need for earthquake. But I injected it because with this skinny building, I just visualize one other, those 1,100 occupants. They're going to call me middle of the night, Mr. Yee, is my building safe? The coffee cup is shaking and spilling on the table. I want to sleep good, so I told the client, I'm going to have to design for earthquake. But if I told him about designing for human comfort, then how does that happen? How do you do that, But all I know is that I took an earthquake, and then I checked the lateral translations and felt that it was safe enough for comfort of living. Now, here is the key, one of the greatest keys. This is a shear wall you saw, on one side of the corridor, and shear wall on the other side of the corridor. This is the corridor here. And wherever you have the corridors and the floor slabs on each side of the corridor, I join these slabs together with what we call a coupling beam. In other words, if you had two independent shear walls, they would rock independently. If I don't couple the shear walls for this earthquake, the lateral deflection on the top will be 853 millimeters. It's just about 3 feet. But if I couple it, it goes down to 460, which is about half. And for wind, the maximum wind, if I don't couple it, the deflection will be 402. We can't place the beam, but in the beam we put special reinforcing steel with links and all that, so you can take bending moment both ways, reversal and all that. But in our computer output, some of the coupling beams were so high you cannot get enough reinforcing steel in there. So I put a huge I-beam, thick flanges, thick webs, which is much stiffer, heavier, stronger, and put that in along with some reinforcing steel and closed ties. And so there were about maybe 14 different locations we had to do that because of overstress in those areas. But without modern digital computers, you can't do this. Fortunately, we have close connections with Dr. Wilson in University of California. He's the author of ETABS and SAP 2000, and most engineers in the world use those programs. But we still got to go to him for that advice. So another feature is there are certain floors where we have double floor height. See, the floor-to-floor height, the typical, is 3.2 meters. But we have some that are 6.4 meters. That's over 20 feet high. Those floors are for mechanical equipment. Huge air conditioning ducts, air handling units. You gotta have high ceilings. But the people, the headroom doesn't have to be, higher than about 6.5 feet. So what we do is maximize the depth of the beam there. We call it a mega coupling beam. And we can maximize wherever you can. You can do it here, here, and up there. Yeah. Wherever you can do it, put it in, and crank it into calculations, and you'll see that you have a lot of benefit from it. Now, down on the ground floor, you have the lower floor, you have certain restrictions. We have to build this passageway for the public because there's a park here, and the public can walk through the building, access to the park. And this is 14 meters wide or something like that. It's very, very wide. And so we have what we call, and other entrances and all that, we have what we call a soft floor. If the walls went straight to the ground, like most typical walls, fine. But some of them get interrupted before they hit the ground. Then you got some huge stresses. In other words, the amplification of stresses. Imagine this thing is 840 feet high, and if you grab the top of it, and you, like the earthquake or the wind or something, you're going to magnify the stresses here, huge one, big time. So instead of making this out of 6,000 pound concrete like we do here, we use 12,000 psi concrete. We call it grade 80. And these are some of the analysis that, led us to, no matter how much steel you put in, you got to increase the concrete strength, and you got to put a lot more steel. So all of these I'm doing so that I don't get called tonight.
Can I ask what the blue is?
That's a point of very, very high stresses. You can't see it, but there's a column here. This column here is over here. And this whole wall, when you crank it this way, you see it's pulling. If you crank it this way, this guy's pushing. And your concentration of stresses is so high there that we have to strengthen it. And we take this big column. In fact, this column, it looks ugly because it's 4 foot square. In other words, 4 feet by 4 feet. And the rest are only 2 feet by 4 feet, So you have the exaggerated column is like a guy with a splint on his leg or something. But you got to have that because, and when you run through the formulas, we run across an item called the omega factor, the omega sign. And in this case, it's 2.3. In other words, whatever you calculate for the load, multiply by 2.3 times. That's based on, mathematical research. So these factors are not well known to most engineers because they take into consideration the amplification, the rhythmic, the pounding forces and all that. And so you automatically have to do some, provision for highly increased stresses. Then wind tunnel testing. This is a wind tunnel testing with the existing buildings in the area, and wind tunnel testing for future buildings around there. In other words, we don't know when the future is coming in. So it might be like this for 10 years, or it might be like this for 10 weeks, and then they start building. So you got to provide strength for both situations. And the results. This is the tall tower. This is the one that's 70 stories high. The wind results, what we call the milli-Gs, is what we measure accelerations. As you blow the wind at different angles, this is the way the accelerations are. The magnitude of the accelerations, like the outer circle represents 16 milli-Gs. That's like 0.016 gravity force, or 1.5%, 1.6% gravity. And so if it's a 10-year 1% damping, you get less restraint, so the accelerations are bigger. If it's a 10-year 1.5% damping, that means you have more restraint. So the red line is where would be the acceleration curve. We know that from the studies that somewhere between 16.7 and 18.9 milli-Gs, you have the threshold of human awareness. The threshold, you start feeling it, people start complaining, you call the building manager, call the engineer. But notice that we don't have anything going up to 16. So we kind of saved it. Right up to about 15 and a half was the 10-year. Of course, that doesn't say you may have a 20-year reoccurrence, which is bigger. Then you're going to have, but hopefully you get a call once in 20 years, not so bad as once every 10 years. And this is the lower tower, the one that's truncated on one side with the subway tunnel, mass transit tunnel. And that's the maximum is somewhere around 11 or something like that, but well below the 16.7 to 18.9. So we're comfortable because the wind velocities in Singapore are not like Guam or Honolulu. In Guam we designed for wind forces like 85 meters per second. Over here is like 10 meters or something like that.
But you're completely out of the hurricane zone there, aren't you?
Yeah, because you're near the equator.
Yeah.
Once can tell you that along the equator, no hurricane, but that's where they're born. So this is where, we have summary of the response to wind tunnel testing, accelerations. That's a human comfort thing. Okay. The real effects in wind tunnel testing, what we always find out is we walk in the open air lobby and all that. Wow, the wind is rushing all over. Women's skirts blow up, that kind of thing. But no buildings fall down. Now, we talk about architects, doing iconic buildings and making us miserable engineers, make us work harder for our fees and all that. But for the first time in my life, I realized that there's a benefit to it. That is, when they finish the project manager, representative over said, "Hey Al, I'll do 01 for you because you worked on the building." And I said, "Well, us engineers, we know how to build them, we know how to design them, but we don't have enough money to buy them." They were selling for $1,000 a square foot. And us poor engineers, 1,000 square foot apartment is $1 million.
Yeah.
And that could be any floor. And that's the minimum. And so they were selling from, I think it ran from about $900 to $1,100 a square foot. I turned it down. To this day, my wife would never forgive me for stupidity, not for anything else that I did. But then, and so they said, "Wow, the thing sold out in 1 week, 600 units." They must have underpriced, so they waited 3 months and raised the price to $1,800 to $2,000 a square foot, and it sold out in 1 day.
Ooh.
Now, who's wrong? The first guy or the second guy, But the biggest mistake is guys like me. I stayed away from all that crazy stuff. And the people who bought, reselling for $4,000 a square foot. So that tells you something.
I don't know what, though.
It takes money to make it. But it also tells me this. Singapore has a government. It's so clean. If you buy lunch for one of these guys, or take one a trip to Las Vegas or something like that, that guy gets canned. But his salary is like $1 to $2 million a year. I'm a minister in government work. They make sure that they're bribery proof. So here's people, oil drillers in Indonesia, and Indian multimillionaires. They all come down to Singapore, buy these apartments, put their families there, or at least have it empty, but they can move in any time. It's the safest place in the world to live. And income taxes, maximum like 15%. I mean, you're talking about the country who knows how to keep people there. And so it's so profitable to do business there. It's so safe to keep your family there, even if they don't do business. You can walk in the street at night and nobody mugs you. If they do, wow, I hate to be in a Singapore jail. But this is the kind of thing that clean government is so important. I mean, you could say, wow, we raise the taxes, we do this, we put incentive for business. The biggest incentive is security. And you know that you don't have to bribe. In fact, if you bribe, you're in trouble. and in the other countries, much more wealth, material wealth, neighboring like Indonesia, Malaysia, and all that, they're so poor. I mean, the people, the downtrodden people are so poor. And the rich get richer and the poor get poorer, and some of the rich get poorer too because they get taken down. But I just want to mention that this part of the world that we're in, this time in history, a lot of lessons to learn from this. Okay.
How many square miles is Singapore?
200. It's the size of Molokai.
We have 4 or 5 million.
We got 5 million people there. When I started there as a consultant to the housing board, we built houses so fast, precast. They were 3 years behind schedule. And about 4 years later, we not only wiped out the 3-year backlog, we had 40,000 finished condos, no takers. We overshot the population. Then the Prime Minister said, hey, don't stop, keep on building. He said, he looks at the demographics, the marriageable age is getting big. We're going to have a huge avalanche of young couples. And young couples, they all move out of the family home because the daughter-in-law can't stand the mother-in-law. They don't want to share the same kitchen. They don't want to eat the same food and all that. I mean, they're very filial, but they want privacy. And they want their own life, and they all make good salaries.
This is way out in left field, but I'll never forget the failure mode of the World Trade Center. The way, after about a half an hour, the thing collapsed like a telescope. What on earth? How did that happen? Can you avoid that thing?
I know the people who designed it. And they followed the code. They did everything proper. But the code has to be changed. The things about code, they're written by guys like us, and we're not infallible. They take a steel beam or steel column, clad it with dry chipboard and plaster, put it in the furnace for 4 hours, put a load on the column, it doesn't buckle. Oh, that's good for 4-hour fire. That's all fine and dandy. This building is good for 4-hour fire. But if an airplane comes in and 23,000 gallons of diesel fuel explode and blows off all the skin off the column, and the steel is naked, and the flames are licking it, at 800 degrees, that steel turns to butter. And so, what chance do you have? That's the problem. And when one floor starts to collapse, the acceleration forces on the next floor and the next floor gets bigger, bigger, and bigger because you keep accumulating additional load as you go down. And I'll tell you, it was just, I felt so bad for it. Yes.
Mr. Yee, we've survived as an organization for over 100 years because we officially leave or stop the official meeting at 1 o'clock. Therefore, it gives me pleasure to present something you've never had before, I'm sure. And you're being photographed for posterity.
Thank you.
Thank you. I call the official meeting to a close, but we may unofficially resume.
Engineers and architects of Hawaii welcome your comment on this program and any of our recent programs. We encourage your direct participation in this community outreach, so please email us your comments and ideas at eahawaii@gmail.com.